So good morning everyone. Today I am going to discuss the acid base. In the last video lecture I have discussed the leveling effect. This is the continuing part of the leveling effect. So if instead of water solvent we take mineral acid, instead of water solvent if you take mineral acid in pure acetic acid solvent which is poor proton acceptor as compared to water, it is found acid becomes weak and can be differentiated. Again I tell you, if you take mineral acid instead of water, then what will happen? Here pure acetic acid solvent which is poor proton acceptor as compared to water, it is found acid becomes weak and can be differentiated. How? So this is the acid, this is the base. Now you get acid CH3COOH2 plus, okay, plus Cl minus. OH2 plus means this lone pair of oxygen accept this proton. Okay. So in the right hand side example, acetic acids and Cl minus ions both compete for protons. Okay. So in the right hand side example, acetic acid and Cl minus ions both compete protons, and formal being a poor proton acceptor does it much less effectively than water. Thus HCl in acetic acid solvent, here acetic acid acts as a solvent, appears to be much weaker acid than that in water. This is the very important why HCl acts as a weak acid when the solvent has been chosen for acetic acid instead of water. So here acetic acid, that is called leveling effect, very important. So due to the presence of acetic acid as a solvent, HCl becomes weak instead of water. Okay. So mineral acid in acetic acid solvent follow the order of their strength. Nitric acid less than HCl, less than H2SO4, less than HBr, less than HClO4 minus. So HClO4 not minus. So nitric acids less than HCl, less than H2SO4, less than HBr, less than HClO4. Okay. Now a weak base like acetamide or acetanilide in aqueous medium cannot be titrated with acid. Okay, a weak base like acetamide or acetanilide in aqueous medium cannot be titrated with acids. If, however, the weak base is taken in glacial acetic acid solvent, the former behaves as a strong base and can be titrated. This is because acetic acids, which acts as a better proton donor, exert a leveling effect on the base. That is very important. A weak base like acetamide or acetanilide in aqueous medium cannot be titrated with acids. If, however, the weak base is taken in glacial acetic acid solvent, the former behaves as a strong base and can be titrated. This is because acetic acid, which acts as a better proton donor, exert a leveling effect on the base. Okay. So these are the some species of molecules having conjugate acids and conjugate base. Okay. So of Bronsted acid. So this is the water with conjugate acid H3 positive. That will come as a MCQ question. What will be the conjugate acid of water? Okay, you have a 4 option or conjugate base of water. So we should remember and you should know the logic. So this is the OH minus, similarly HCO3 minus, H2CO3, CO3 2 minus, similarly HCO4, HSO4 minus, H2SO4, SO4 2 minus, similarly NH3, NH4 plus, NH2 minus. Now what are the limitations of Bronsted-Lowry concept? It fails to explain the substance like L16, BF3 and SnCl2 which acts as a weak acid behave as an acid although they do not contain any hydrogen, hence cannot give a proton. So though they act as acids, but they didn't have any H plus ions. Okay. Acidic oxides such as anhydrous, carbon dioxide, SO2 and SO3 etc. can neutralize basic oxide like calcium oxide, barium oxide even in the absence of solvent. So this type of anhydrous can neutralize basic oxides like calcium oxides and barium oxides even in absence of solvent. Okay. So now Lewis acids and base. G.N. Lewis gave a new concept in 1923 which eliminated the necessity of electrons while base is a which necessity of a proton. So G.N. Lewis gave a new concept in 1923 which eliminated the necessity of a proton. The acid and base may be defined as follow. Acid is a substance which can accept a pair of electrons, while base is a substance which can donate a pair of electrons. So acid is a substance which can accept a pair of electrons and base is a substance which can donate a pair of electrons. So according to Lewis acid and base, that is the definition of acid base. Acid means accept a pair of electrons, base means donate pair of electrons. This concept is also called electronic concept, according to which a Lewis base donates an electron pair to be accepted by Lewis acids. The two get linked to each other by coordinate bond. Now types of Lewis bases. Neutral molecules with at least one lone pair of electrons which they can easily donate. So types of Lewis base. The neutral molecules, okay, with at least one lone pair of electrons. You see NH3 having one lone pair of electron, RNH2 having one lone pair of electron, ROH having lone pair of electron, H2 having lone pair of electron. Okay. Negatively charged ion or anions, F minus, Cl minus, Br minus, OH minus, Cl minus. So these are the Lewis base. Lewis base means they must have or possess lone pair of electrons. Not only lone pair of electrons, sometimes negative charged ions also acts as a, or anions acts as a Lewis base. Okay, so here BF3 plus NH3, we get the BF3 NH3 adduct. Electron deficient species like Al-Cl3, cobalt 3 plus, Mg2 plus etc. can act as a Lewis acids, while species like water, ammonia, OH minus etc. which can donate a pair of electron can act as a Lewis base. So from these examples we can say that these species are acts as a Lewis acids and this species acts as a Lewis base. Okay. Now types of Lewis acid. As you know, Lewis base means having lone pair of electron, either lone pair of electron or negative charge. Okay, negative charged ions or anions. Now types of Lewis acid. Molecule in which the central atom has incomplete octet. Molecule in which the central atom has incomplete octet, LCl3, BF3, APCl3. These acts as a Lewis acid. LCl3, here BF3 acts as a Lewis acid. Okay, and these are the Lewis base. So simple cations, most of cations of D block in general are Lewis acids because they are deficient in electron. So most of cations of D block in periodic table in general are Lewis acids because they are deficient in electrons. As for example, Ag plus, Cu2 plus, Ap3 plus etc. So what will happen if Ag plus Lewis acids, okay, react with Lewis base ammonia? What will happen? They will form this compound, okay, through coordinate linkage. Molecules in which the central atom of P block has empty d orbital. These molecules can accept electron pair to be kept in their empty orbitals. As for example, SnCl4, SiF4 etc. So as you know, SiF4 Lewis acid, okay, acts as a Lewis acid, plus twice F minus acts as a Lewis base. We get SiF6 minus complex. Number 4, molecules in which atom of different electronegativity are linked by multiple bonds. Molecules in which atoms of different electronegativity are linked by multiple bonds. Okay. CO, carbon monoxide behave as a Lewis acid because the oxygen atom are more electronegative, than the carbon. Therefore, carbon atom becomes electron deficient. So that's why oxygen withdraws electron clouds toward itself and possessing negative charge on it. Similarly, being a less electronegative carbon compared to oxygen, it possesses positive charge. So CO behaves as a Lewis acid because of oxygen atom being a more electronegative than carbon. So carbon atom becomes electron deficient. So what are the limitations of Lewis concept? It fails to assign the strength of acid and base. Number 1. Number 2, according to this concept, the acid-base reactions should be accompanied by the formation of dative bonds, but no such bonds are formed when acids like HCl, H2SO4 and nitric acids reacts with NOH or KOH. What will happen? Drawbacks of 2. According to this concept, the acid-base reactions should be accompanied by the formation of dative bond, but no such bonds are formed when acids like HCl, H2SO4, nitric acid reacts with NOH and KOH. Okay. Number 3, acid-base reactions are usually fast. But the formation of dative bond is slow. So formation of dative bond is slow process. Catalytic property. Number 4, catalytic property of the acid is due to H plus ions furnished by them, but the Lewis concept doesn't permit any such property. Again I tell you, this is very important limitation of Lewis concept. It fails to assign the strength of acids and base. Number 2, according to this concept, the acid-base reaction should be accompanied by the formation of dative bond. Okay, in the coordinate compound we have seen the dative bond, but no such bonds are formed when acids like HCl, H2SO4 and nitric acids react with NOH or KOH. Acid-base reactions are usually fast, but the formation of dative bond is very slow. Catalytic property of the acids is due to H plus ions furnished by them, but the Lewis concept doesn't permit any such property. Okay. Next, factors affecting acid strength. So what are the factors affecting acid strength? So weaker the H bond, okay, weaker the HA bond, more easily it gets dissociated to give H plus ions. Weaker the HA bond, higher the HA bond, so more is the HA bond means hydrogen can easily abstract it. Okay, so if the bond between H and A is weak, then abstraction of H will be more facile. So more easily it gets dissociated to give H plus ions, and hence stronger is the acid, as for example HI and HBr. So similarly, get at the polarity of the HA bond, get at the polarity of HA bond, the polarity generates due to the difference of electronegativity. Higher the electronegativity difference, greater will be polarity. That is, larger the electronegativity difference between the atoms H and A, more easily the bond breaks, and hence greater is the acidic strength. For elements in the same group of periodic table, the bond strength dominates over the polar nature. So for the element in the same group of periodic table, the bond strength dominates over the polar nature. Thus, down the group, as size of the atom increases, bond strength decreases, size increases. As I discussed, so many video lectures in modern periodic table. Why size increases? Okay, due to the incorporation of electron into the new quantum cell. Okay, principal quantum number changes. So if size increases, then attraction of nucleus on outer shell electron will be less. So bond strength decreases and hence acidic strength increases. For example, for the element of group 17, that will be the acidic. Okay. So HF less than HCl less than HBr less than HI. So acidic strength increases from left to right. So from left to right acidic strength increases. Why? Size of the iodine increases more. Half the size of iodine, bond strength between the iodine and hydrogen is very less. So if bond strength less, that means nucleus, force of attraction from nucleus and outer shell electron decreases. So hydrogen can be easily abstracted from HI. So acid strength increases from left to right, that is HF to HI. Similarly, for the elements of group 16, acid strength increases as water less than H2S less than H2SC less than H2Te. Same explanation. So for the elements along the same period, however, the polarity of the HA bond decides the acid strength. With increase in electronegativity of A, the polarity of the bond increases, hence the acid strength also increases. Okay, we consider here second period element of the same period. You see, this is the second period element: carbon, nitrogen, oxygen, fluorine, neon, etc. So this is the p block element: boron, carbon, nitrogen, oxygen, fluorine. So electrons from left to right, from left to right size decreases as effective nuclear charge increases. So fluorine is more electronegative atom. So HF polarity is more. So being fluorine is more electronegative. So acid strength, the electronegativity and polarity also increases. So all the three parameters, acid strength, electronegativity and polarity also increases when you move from carbon to fluorine, having a compound CH4 less than NH3 less than water less than HF. Okay. Now the dissociation constant is presented by, we know dissociation constant K H3 positive, molar concentration of H3 positive into molar concentration of OH minus. Because if you consider water plus H plus, then what will happen? Okay, water gives protons, another water molecules to form a hydronium ions. So this is the dissociation constant. So concentration of water is omitted from the denominator. So this is the denominator, as it's taken as a solvent, a huge amount, so its concentration is taken to be unity. So as water is pure liquid and its concentration remains constant, so molar concentration is incorporated within the equilibrium constant to give a new constant which is known Kw, which is called the ionic product of water. That is Kw equals to molar concentration of H plus and molar concentration of OH minus. So concentration of H plus and has been found that experimentally 1 into 10 to the minus 7 molar at 298 Kelvin or 25 degrees centigrade. And as dissociation of water produces equal number of H plus and OH minus ion, because if water gets dissociated, we get H plus and OH minus ions equal number. So Kw equals to, we can write 1 into 10 to the minus 7 whole square equals to 1 into 10 to the minus 14 whole square. So acidic, when it will be acidic? When H plus concentration greater than OH minus. Neutral, both the concentration same. Basic, when H plus concentration less than OH minus ions. So next, what is the pH scale? So pH scale, this is the power of hydrogen. pH scale, concentration of H plus ions, is written in a simple form introduced by Sorensen, known as pH scale. So pH is defined as the negative logarithm to the base 10 of activity of H plus ions or molar concentration of H plus ions. Negative logarithm to the base 10, okay, of activity H plus ions. So pH equals to minus log activity H plus, where activity H plus is the activity of H plus ions, or we can write so minus log of CH plus base to the power 10. You see here minus log to the power base 10 H plus ion concentration, third bracket means molar concentrations, minus log CH3 positive, H3O positive, or if you remove minus, then log 1 by H3O positive. So with increasing H plus ion concentration, you see pH decreases. Okay, so pH increases means H plus concentration decreases. Now the pH scale was marked from 0 to 14 with central point at 7 at 25 degrees centigrade, taking water as a solvent. If the temperature and the solvent are changed, the pH range of the scale will also change. 0 to 14 at 25 degrees centigrade, where the value of ionic product Kw 10 to the power minus 14 and neutral point pH 7. If you consider 0 to 13 scale, then what will happen? At hot temperature 80 degrees centigrade, then you get the Kw value 10 to the minus 13, and then the neutral point also has been changed, pH equals to 6.5. pH scale can also be negative, okay, or greater than 14. Thus, pH of solution may be defined as the logarithm of reciprocal hydrogen ion concentrations. Similarly, in case of pOH, we are considering OH minus, what will same minus log for molar concentration of OH minus, or we can write pKw equals to minus log Kw. So, pH scale, it is the range of expressing the nature of any solution. So we know that at 29 Kelvin, H3 positive molar concentration ranges from 10 to the power 0 molar to 10 to the minus 14 molar. We know 0 to 14 scale, general scale at 25 degrees centigrade. If any asks what at 80 degrees centigrade, pH scale what is the 0 to 13 and neutral point 6.5. When you consider 0 to 14, neutral point is 7. Thus, for neutral solution, H plus concentration 10 to the minus 7 and pH 7. For acidic solution, H plus concentration greater than 10 to the minus 7, so pH less than 7. Acidic means pH less than 7. So basic solution, H plus less than 10 to the minus 7, that is pH greater than 7, so that is basic solution. pH greater than 7 basic, less than 7 acidic, and equals to 7 neutral solution. So this is the pH scale, H plus concentration is pH scale. You see this is the neutral zone, 10 to the power 7, increasing basic character, increasing acidic character. So this is the corresponding scale. Okay. So now for an again consider the ionization constant of water at 29 Kelvin. Kw equals to H plus ion concentration, OH minus concentration, which is known as a 10 to the minus 14. Taking negative logarithm on the both side of the equation, we have minus log Kw minus log this, so minus log H3 positive minus log OH minus, that is minus log 10 to the minus 14, or pKw equals to pH plus pOH equals to 14. Remember, pKw equals to pH plus pOH equals to 14. Kw changes with temperature and the pH scale also changes. Okay. Next, this is the pH of some common substance. Saturated solution of sodium hydroxide 15, 0.1 molar sodium hydroxide 13, lime water 10.5, milk of magnesia 10, egg white and sea water 7.8, human blood 7.4, important for MCQ, and milk 6.8, human saliva 6.4. These are the pH scale of some fluid. Okay, and the rest of the part will be discussed in the next slide. Now come to the point buffer solution. The solution which resists a change in pH value on the addition of small amount of strong acid or base less than 1%. So solution which resists a change in pH value on the addition of small amount of strong acid or base less than 1% to it or when solution diluted is called buffer solution. So types of buffer solution. There are two types of buffer solution. These are simple buffer solution, the solution of the salt of weak acid and weak base. Ammonium acetate, the ammonium formate, ammonium cyanide acts as a buffer solution. Now buffer action of simple buffer solution. Ammonium acetate decompose to or dissociate into CH3COO minus plus NH4 plus. If strong acid HCl is added, how buffer action operate? Now this is the electrolyte ammonium acetate dissociated into ammonia acetate ions plus ammonium ions. Now if you add in this solution HCl, what will happen? HCl dissociated into H plus plus Cl minus. Now H plus will combine with these acetate ions. This H plus combine with these acetate ions to form acetic acid, which is a weak acids and will not further ionize. So there is a no rise in H plus and concentration and pH remain constant. Clear? So there is no rise in further H plus and concentration and pH remain constant. So acetate ions H plus we get acetic acid, which is a weak electrolyte. So there is a very little tendency to dissociate into ions. So that's why the solution pH remains constant if you add HCl. Okay, which acts as a strong acid. Now if a strong base is added like sodium hydroxide, what will happen? NO is dissociated Na plus OH minus and ammonium hydroxide dissociated ammonium ions plus OH minus, these ammonium ions. Okay, now these ammonium ions combines OH minus to form ammonium hydroxide. So this is also weak base. This change in OH minus concentration is resisted by ammonium ions by forming ammonium hydroxide, that is also weak base. So our motto is buffer solution and action of the buffer to resist the change in pH. If you add strong HCl, then H plus combine acetate ion to form acetic acid, which is weak. If you add sodium hydroxide, now OH minus combine with ammonium ions to form ammonium hydroxide, which is also weak base. So thus we can resist the change in pH. So we know pH equals to formula, you just know the 7 plus half pK minus half pKb. Now mixed buffer solution. There are further two types of acidic buffer solution whose pH 4 to 7. It is in mixture solution of weak acids and salt of this weak acid with a strong base. For example, acetic acid plus sodium acetate. This is the strong, this is the weak. And another example, oxalic acid and potassium oxalate. So acetic acid dissociated into acetate ions plus H plus ions, weakly ionized as it is a weak electrolyte. But sodium acetate being a strong electrolyte, it dissociated acetate ions plus Na plus ions, strongly ionized. When a few drops of an acid HCl are added to it, the H plus ions from the added HCl combine with the acetate ions to form acetic acids. Thus there is a no rise in H plus ion concentrations and pH of the solution remains constant. On the other hand, when a few drops of base sodium hydroxide are added, the OH minus ion of the acid, OH minus of the added base reacts with acetic acid to form ionized water and acetate ions. This one, acetate ions and water, undissociated water. Thus there is no increase of OH minus concentrations and hence pH of the solution remains constant. So this is the two types of buffer solution, very important. Acetic acid, okay, dissociated into this, and sodium acetate dissociated into this strong electrolyte. Now if you add HCl, what will happen? If you add sodium hydroxide, what will happen? So pH remains constant. So this is the another form. Henderson equations for acidic buffer solution, pH equals to pK plus log salt by HA. Okay, similarly, or we can pH equals to pK plus log salt by acid. Okay, same thing which shown two different way. Either A minus, that is salt by acid. This is the Henderson equation. Now basic buffer solution pH 7 to 10. It is the mixture of solution of weak base and salt of this weak base with a strong acid. For example, ammonium hydroxide plus ammonium chloride, human blood. Okay, basic buffer solution. Basic buffer solution consists of mixture of weak base and its salt with strong acid. Best known example, ammonium hydroxide and ammonium chloride. We know ammonium chloride dissociates into ammonium plus and Cl minus. It should be Cl minus. Okay. It should be Cl minus. Highly ionized ammonium hydroxide, it is weakly ionized due to weak base. When a few drops of base sodium hydroxide are added, the OH minus ions form NOH combined with ammonium ions to form feebly ionized ammonium hydroxide. As you know, ammonium hydroxide is weak base, thus there is a no rise in concentration of OH minus ions, and hence the pH value remains constant. So OH minus ammonium ions, we get ammonium hydroxide. Okay, when a few drops of HCl are added, the H plus from acid combine with ammonium ion. These H plus ions combine with ammonium ions to form again ammonium ion and undissociated water molecules. So thus the addition of acid does not increase the H plus ion concentration. Hence pH remains unchanged. Okay, so this is the pH of black coffee, 5 point tomato juice, soft drinks, lemon juice, glacial juice, etc. Okay, and this is the pH of basic buffer solution, Henderson equations, pKb plus log salt by base. Okay, now acid base indicator. Acid base indicator indicates whether the solution is acidic or alkaline and cannot be used for determining the strength of acid or alkaline solution. Phenolphthalein, methyl orange. I have shown here indicator phenolphthalein, pH range 8.3 to 10.5, color range colorless to pink, phenol red 6.8 to 8.4, yellow to red, methyl orange 3.2 to 4.5, pink to yellow, methyl red 4.4 to 6.5, red to yellow, litmus 5.5 to 7.5, red to blue. So now this is the very important problem. Calculate pH of 1.10 to the minus 8 molar HCl solution. So maximum students did wrong answer. How? Now they give the answer 8. Okay, but it is actually not. HCl pH not 8 because it is the base. So that's why you should consider the dissociation of water molecules. So dissociation of water molecules like H3 positive plus OH minus, so Kw ionic product. In the previous slide I have discussed this one. Now X with the concentration of OH minus and H plus ions from water, then H3 concentration is generated on equations from the ionization of HCl dissolve. So like this way, HCl, H2, this one, and 2 from the ionizations of water. Okay. So in this very dilute solution, both the source of H3 positive must be considered. So here HCl H3 positive, here also H3 positive should be considered. So that's why H plus concentration not only 10 to the power minus 8, most of the student did mistake. So it should be 10 to the minus 8 plus X, that is the funda. So H plus molar concentration, you should consider the dissociation of water molecules. So Kw 10 to the minus 8 plus X into X into 10 to the minus 14. So X square plus 10 to the minus 8X equals to this. Okay, 0. So OH minus concentration 9.5 10 to the minus 8. So pH 7.02 and pH 6.98. So this is the very important problem. So we should consider the dissociation of water molecules in this type of problem, because if you put the concentration of H plus ions direct 10 to the minus 8, then we get the pH value 8, which is not thus within the permissible limit 0 to 7 or less than 7, but it is 8 means it is basic, but not like that. You should consider the dissociation of water molecules. So then the final concentration of H plus will be 10 to the power minus 8 plus X. Then you get from Kw equations, you get the value of OH minus concentrations, then you get the pH. You know pH plus pOH equals to 14. So if you get pH value 7.02, then you can find out the value of pH. So pH equals to 14 minus 7.02. So in this way you can find out the pH of this such type of very important problem. So I hope you are enjoying this video lecture. So thanks for watching this video.